Alright, so now I'm going to do example 7 in the note. Okay, so first let us find the eigenvalues. So pause the video and try to find the eigenvalues by yourself. Okay, so we want to write a minus lambda I. Now I'm going to write this very fast, quickly. A minus lambda is going to look like 2 minus lambda 0 1 0, 2 minus lambda here 1 1 1 1 minus lambda. Okay, so now we want to find the determinant of this. Now feel free to pause and think. Okay, so let's find the determinant. So what I do is I take the first row and I go element by element. So I take 2 minus lambda times the determinant of this part, which is 2 minus lambda 1 minus lambda minus 1 times 1 1. Now by default here you have negative. The second term will be 0 because 0 times everything doesn't matter because you multiply by 0. So I just don't care about that part. And then plus by default, and the third term is 1 times the determinant of this part, which will be 1 times 0 is 0, 0 minus 1 times 2 minus lambda. Okay, so this is what we get. We need to make it equal to 0 so that we can find the roots of lambda. So let's simplify. So if you simplify here, 2 minus lambda times, let's wait a minute, maybe. So 1 minus lambda minus 1, here minus, okay, here minus, here plus 1, it's minus, anyway, 2 minus lambda. Now here we can save a lot of time if you let this term be like this, and you can see from this term versus this term you can factor out a 2 minus lambda, right? So that makes our life easy so that we do not approach to a cubic equation. But if you feel like you don't see that, you feel free to expand this, multiply all these brackets out and get a cubic equation and solve the cubic equation just like I taught you to find the roots of a cubic equation. Okay, so if I factor out the 2 minus lambda, from this term will be left, that is 2 minus lambda 1 minus lambda minus 1 minus, here you took a 2 minus lambda, so it's minus 1 here. So let's simplify. So it seems to be like 2 minus lambda here. Inside, anyway, we have to expand this. So let's multiply this out. So 2 times 1 is 2 minus 2 lambda minus lambda plus lambda square minus 1 is equal to 0. So 2 minus lambda, here it seems to be like minus 1 minus 1 minus 2. That minus 2, this minus 2 and this 2 cancel out. So that is like 2 minus 2. So it is here 3 lambda minus 3 lambda plus lambda square. Okay, we are almost done. We can take a lambda out here. So 2 minus lambda, if we take a lambda out here, minus 3 plus lambda is equal to 0. So we get our eigenvalues finally. So our eigenvalues are like 0, lambda 1 is 0, lambda 2 is 3 from here, not negative 3 from here. The third eigenvalue from here is 2. So we have our 3 eigenvalues. Okay. Alright, so now we want to find eigenvectors to solve this differential equation. So let's find our eigenvectors. So let's first take the first eigenvalue, 0, lambda 1 is equal to 0. Now feel free to pause and do it by yourself. That is how you exactly should do these problems. Okay, so we want to write a minus lambda I. Here it's a minus 0 I, which is a minus nothing. It's just a, right? 0 times I is 0. So it's just you are working with a. So you want to solve a is actually 2 0 1 0 2 1 1 1 1. You want to solve this equation for little case and find that eigenvector, right? Again, a minus lambda is a, so you want to solve ak is equal to 0 equation, right, to find the eigenvector. Now we use the Gaussian elimination because that's the convenient and the easiest. So 0 2 1 0 1 1 1 0. Now what would you do first? First look at the pivot position. Here pivot position is 2. Now what I would do is, it's a non-zero number, which is good, but ideally I would like to have it 1. But I don't divide by 2. Instead of, I will become smart and switch R1 with R3. So swap R1 and R3. So this will be like 1 1 1 0, 0 2 1 0, 2 0 1 0. Okay, otherwise you can divide by 2 this, you can divide that R1 by 2, but the problem is you will have half here, then the half here, so that will be a fraction. I don't like to work with fractions when I have Gaussian elimination. Okay, all right, so now this is the pivot position, it's 1 ideal. Now you want to make this to 0. So what you can do is you can multiply the R1 by -2 and add it to the R3, but in the process you don't change R1, right? 1 1 1 0, 0 2 1 0, second row doesn't change. So if you add, the purpose is to make it 0, right? -2 plus 2 is 0, -2 plus 0 is -2 here, -2 plus 1 here is -1. So this is what we get. Now we go to the second pivot position because we have zeros here. So second pivot position is 2. Now here this is ideal. Now you don't need to have 1. It's not necessary. If it is 1, it's perfect, but you don't want to create, at the same time you don't want to create fractions also. Okay, so I would avoid dividing by 2. Anyway, what I really want now is to make this -2 0. So what you can do is R2 plus R3, right away you get 0, right? 1 1 1 0, 0 2 1 0, 0 0 0 0. That's the advantage. Okay, so if you do this in the smart way, your life becomes so much easy. Anyway, so we now move on to the third pivot position, and at this point we don't really care, right? Okay, so let's write the matrix form again. So 1 1 1 0 2 1 0 0 0. You have to solve this for k1 k2 k3 equal to 0 0 0. Okay, so that is what we did. All right, so now let's multiply out. Now let's multiply this row by column. So it's k1 plus k2 plus k3 is equal to 0. Here 2k2 plus k3 is equal to 0. So those are the two equations. Now we want to make relationships here. So here from these two, k2 is actually -k3 over 2, right? From the second equation. From the first equation, k1 is -k2 minus k3 if you take k2 and k3 to the right. Okay, so now choose k3 smartly. What would you choose for k3? I would choose -2, right? If k3 is -2, k2 becomes 1. Then k2 is 1, means here -1, here plus 2 because of this negative. So k1 is also 1. So our eigenvector is 1 1 -2. Okay, so that's the eigenvector related with the eigenvalue 0. So that's done. All right, so let's go and find the second eigenvector. So we are using the eigenvalue 2 now. So A is 2 0 1 0 2 1 1 1 1. Now you want to find A minus lambda I. That means A minus 2i. So let's find it. So A is 2 0 1 0 2 1 1 1 1 minus 2 times I is 2 0 0 0 2 0 0 0 2. Now pause it and try to do it. Okay, try to find these eigenvectors by yourself. Here if you subtract 0 0 1 0 0 1, yes, and here 1 1 1 minus 2 is -1. Okay, so this is okay, so this is the A minus 2y. Now this is easy. Okay, so we want to now solve the equation 0 0 1 0 0 1 1 1 -1 k1 k2 k3 is equal to 0 0 0. Now pause here. Now do you really want to do Gaussian elimination for this system? Now it's almost, you don't need. Now at this point you have to pause and think. Okay, see how simple this matrix is. 4 terms are 0, and you can see already, you can see k3 is 0. Can you see that? Let's write down the equations here. Okay, really these two rows are same, and it directly give you k3 is equal to 0, right? right? So then the last equation gives you k1 plus k2 minus k3 is equal to 0. We know k3 is 0, so k1 plus k2 is equal to 0, means k1 is negative k2, right? So choose a value for k2. Let's choose k2 to be 1. So k1 is negative 1. So our eigenvector is negative 1, 1, 0. So here we didn't need to do the Gaussian elimination because what we got here is very simple, okay? But if you were to do the Gaussian elimination, that's also encouraged to do, right? If you feel comfortable with it. Don't get confused because you will get the same answer. Here, actually, if you were to do the Gaussian elimination, you will swap R3 with R1, then you will immediately see you already have done all the steps. You just need to swap R3 and R1 then to make the pivot position 1. Then you will see you don't need to actually do anything, okay? All right, so that's done. That was so easy because this matrix was so simple by the nature. Now the third eigenvalue. Okay, third eigenvalue was 3. So we need a minus 3i. So a is 2, 0, 1, 0, 2, 1, 1, 1, 1. Now minus 3 times I is 3, 0, 0, 0, 3, 0, 0, 0, 3. So this is like 2 minus 3 is negative 1, 0, 1. Here 0, negative 1, 1. 1, 1, negative 2. Now here, for example, you have to do Gaussian elimination. But then the equation before is, let's be consistent. So we want to solve for little k1, k2 and k3 to get this eigenvector, right? Okay. All right, so let's write the augmented matrix. Here you need to do Gaussian elimination. 0, negative 1, 1, 0, 1, 1, negative 2, 0. Alright, now what would you do? Well, here the pivot position is negative 1. We would like to have 1, but doesn't matter. Negative 1 is fine. We can live with negative 1. So we want to make this 1, 0. So let's add R1 plus R3. So we get negative 1, 0, 1, 0, 0, negative 1, 1, 0. So if you add here, this will be 0, here this will be 1, 1 plus negative 2 is negative 1, 0. Now we move on to the second pivot position because these two are 0. This is negative 1, which is fine, okay? So now you want to make this 1, 0, so add R2 plus R3. So negative 1, 0, 1, 0, 0, negative 1, 1, 0, here 0, 0, here will be also 0, 1 plus negative 1 is 0, 0. So now we don't care about the third pivot position, so we are done with the Gaussian elimination. Okay, so now let's write the matrix equation. Negative 1, 0, 1, 0, negative 1, 1, 0, 0, 0 times little k1, little k2, little k3 is equal to 0, 0, 0. Okay, so now let's write down the matrix equation, the equations out of this matrix equation. So negative k1 plus k3 is equal to 0 from the first equation. From this equation, negative k2 plus k3 is equal to 0. So it seems to be like these two equations. K1 is equal to k3, k2 is equal to k3, right? Nice one. So let's choose k3 to be 1. So then k2 is 1, k1 is 1. So that's the eigenvector. Okay, good. Now we are already done. Almost done. So for the first eigenvalue was 0 and the eigenvector we found was 1, 1, negative 2. Second eigenvalue was 2. The eigenvector we found 1, negative 1, 0. Third eigenvalue was 3. The eigenvector we found 1, 1, 1. So we have all the eigenvectors and corresponding eigenvalues. Then the first solution is of the fundamental set of solution is 1, 1, negative 2 e to the 0t, right? 0 is the eigenvalue, but e to the 0t is 1, so x1 is just this eigenvector. X2 is 1, negative, x2 is 1, negative 1, 0, e to the second eigenvalue is 2t. Third solution is 1, 1, 1 eigenvector times e to the lambda 3 is 3. E to the 3t. So we can write the final solution as xt c1, the first solution 1, 1, negative 2 plus c2 1, negative 1, 0 e to the 2t plus C3 111 e to the 3t, where C1 and C2, C3 are arbitrary constants. So this is the general solution. Now I know it was a long problem, but you can get this type of a question maybe in exam and definitely in homework. But either way, you should know, okay, these are standard procedure of solving problems. So that is how you solve a 3x3 system of differential equation to get the general solution. Okay, all right, thank you.